Hello everyone, welcome to part 2 of lecture week 11's video. And in this part, we're going to talk about an application along with a few other things. So now, first one is cost analysis, right? So let's look at just one example. So if the marginal cost of producing X units of commodity is given by this. So now, what is this marginal cost, right? So we talked about in the previous lectures, well, this measures the sensitivity, right? Sensitivity, so we have two entities. X represents the units of producing X, the units of a commodity, and we have the cost, right, of along with this production. So producing different units will give me different cost. And so, but I want to know how cell dynamics, or how do I vary different values of X change the cost, right? So, and how to measure the rate of change or measure the sensitivity. That's where the marginal cost comes in, or in other words, that's where the derivative of the cost function comes in. Okay, so this is essentially measures the sensitivity of the cost with respect to the input X. Now we have this derivative, which is expressed in this form. And we're also given the fixed cost is 2,000. Fixed cost is 2,000. So what does that mean? That means that if I do not produce anything, right? So if I do not produce anything, my cost is 2,000. So this means that when X equals 0, my cost would be 2,000, right? So this is the fixed cost I have. Now we're asked to find the cost function and the cost of producing 20 units. So naturally, we should first take the to solve for the antiderivative of the marginal cost, right? So how do we solve for the antiderivative of the marginal cost? Let me just write it down. The cost function itself, and it's going to be an integral, right? So doing the inverse. So it's again the cost, the marginal cost multiplied by the units, right? The units increase the differential in X. So what this gives us is this one. So 0.3 X squared plus 2X dx, right? And we know how to take the antiderivative based on the previous video. So basically, what this gives us is that, okay, let me just move it up and then write it down. We just use the rule to decompose it. 3x squared dx plus another differential 2x dx, right? And then we can move the constants outside. So move the constants outside because this is if we do this can make things easier, right? So what we have here is again equal to 7.3. Then if we just take the antiderivative, we have x to the power of 3 over 3, right? Plus c. Here we have 2 again square over 2 plus c. Okay, so now we multiply each term, then we have 0.1 x cube and plus 0.3 c plus here we have x squared plus 2c. Now these are all just constants, right? These are all just constants, so we can just say the final result would be just plus 1 c, right? But this c is actually a bit confusing with the cost, so let me just erase these and then use another symbol which is called k, right? K is our constant, and then we just have one constant key. Okay, so now what is this constant? So this constant can be solved by this condition. So we just equate x with 0, and we have the equation, then we can solve for k, right? So this actually helps us to get the exact value of k. So instead of many infinite number of potential row functions, now with this condition, we can nail down to just one row function. All right, so that's what we have. And the second question, the cost of producing 20 units, which means that's what is the cost when plugging the value of 20 to X, right? Okay, so that's just one analysis. Now let's continue. So reversing the chain rule. So what does this mean? This means that we actually want to plug in the chain rule and say how it impacts our results. So this is our chain rule, which is something we counted earlier. So X first goes to a transformation or the function of I, and then the function of E. So this is a composite function, right? Can also express as a composite function of X, right? And now if we take the derivative, we need to introduce a chain rule, then first the outer layer, then the inner layer derivative. So what do you mean by reverse it? Right, reverse it means that we take this is our derivative, and then we take the antiderivative of the derivative, or take the integral of the derivative function. And what this gives us naturally is gives us the raw function plus the constant c. Right. Now, how to make sense of these results? So one way to understand this is that we can actually express. So I can actually take this as an entity, right? So we deal with this portion first, so and then the deal with this later. So what this gives us, right? By substituting v as a function of I, now we have here. So basically we have the so this will become the integral of, again, the outer function. But we have this, so it's going to be a v, right? A function of v, and then multiply v derivative d x, right? So what is this? It's just dv, right? Because v is a function of x, right? So v is a function of x, then it's a function of x. So v because of this. So because of this, now if you take the derivative of v, then we need to take the outer layer and then the inner layer, which is the x itself, right? So this is what we have. In other words, by treating this as entity, we can actually move I inside, and then we have these results. Okay, so basically that's where things become simpler. Now we just handle this one term. Now, what is this one term? You can just get back the raw function and then plus constant c, and then plug the v back. So this is usually a technique we employ when taking the antiderivative of multiple terms inside. All right, so let's just look at one example and see how it works. Before we look at example, let's look at a few rules first, or formulas. Okay, so first we have the power function and the derivative, the derivative function here. So this here is because it's very familiar face, right? So this actually is the derivative of this term, right? So we can just plug in it back, and we have this extra term here. So this is so if you're not sure about the specific form, I always try to take the derivative of this guy to see if they match with what you have in the integrand, right, of the integral operation. So this is something you can try to plug in and verify. So this is going to be very helpful. Again, similarly, we have this expression function with the additional derivative on the inner function. Then this is the raw function, what it looks like, plus a constant c. So this again, it's similarly, but just remember that we have this extra modulus operation here to ensure that whatever goes inside the lowering function is going to be positive, right? So let's just look at one example, maybe take the second one and see how it works. So now we can, of course, use the formula to plug in, which is this one. But so if you check it out, right? So if you check, so this is so f of x now becomes x squared, right? And then f prime of x becomes 2x, which checks in terms of the form. But we can also work out in a second way, which is that this will actually become, let me just say, this will become integral e to the power of x squared, and then I just have let me see, x squared, right? So x squared, because dx squared is gonna be 2x then dx, right? So this is I'm just expressing it backwards to get this. So now this x squared is an entity, right? So it's an entity, and it basically says that I can re-express it as e to the power of u, and then du, and u is x squared, right? So u is that I'm just adding a variable. So now naturally, the result becomes e to the power of u plus c, and then because u is x squared, then we just plug it back u gets e to the power of x squared plus c, right? So it's going to be the same result. So okay, so that's something, the different ways you can get it, but you can always remember to do the check. So if we take e to the power of square and then plus c derivative, then does that get us the original answer here? So we have if you take derivative, then it's going to be about square, then it's going to be the outer layer multiply the inner layer, right? So this is exactly this one, right? So it gives us the derivative function. So always do the check, so that's to ensure that they are equal to each other. So the raw function, we take the derivative, example the derivative of this function. Okay, so that's it for this video, and thanks for watching.